Hello, everyone. What I want to do today is prove what I mentioned last time, Parseval's theorem, which is just that the Fourier transform is an isometry, and I want to prove Fourier inversion. Okay, and remember from last time that we can define the Fourier transform for a function on Rn in a very natural way. So in particular, 1 second, get my pen out here. Right, so black here. Right, so if I have a function defined on Rn, then the Fourier transform is basically the same thing, except instead of x times u, it's x dot u. And remember, this is just Euclidean dot product x1, u1, all the way plus dot 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 plus xn un. And remember, the Fourier transform has a minus here, and without the minus, you get the inverse Fourier transform. Okay, so before I do anything, I want to make a little bit of a digression on approximations of the identity. So proving a lot of this will be for homework. So let's say I have f non-negative almost everywhere. F is an L1, and the L1 norm equals 1. So what I want to do is, for lambda positive, define f lambda of x to be lambda to the n f of lambda x. So lambda is going to be something big. Usually in textbooks, lambda is 1 over epsilon for small epsilon. But for us, it's more convenient to think of lambda as something large and positive. So by just a trivial change of variables, we get that, well, we get a family of non-negative L1 functions where the integral of each function here is 1. And so it's going to be easy homework. It basically is the same proof as the proof of Fourier's theorem, virtually the same proof. So it's a really easy homework that when I convolve a function, an LP function, with f lambda, as lambda goes to infinity, positive infinity, this is going to be equal to f in LP of Rn. And remember that f convolved with f lambda of x is going to be this integral here. I'll have to squeeze it in. F of x minus y f lambda of x dx. Let me move that over a tiny bit. So the integral f of x minus y, f lambda of y dy. So in particular, what we'll need to use is a Gaussian e to the minus pi x squared. So you don't really have to use exactly this. A lot of people use e to the minus x squared, and you have a normalizing factor here. But this is probably, I think, the easiest to do. So let's check that this has L1 norm 1. Well, first of all, this is just trivially x1 squared. Add all this up. So this becomes just, trivial properties of exponentials, the following product, which makes computing the L1 norm incredibly easy. just using Fubini's theorem, you just integrate this. It's just going to be a product of these one-dimensional integrals. So it's a product of e to the minus pi x1 squared dx1 all the way to e to the minus pi xn squared dxn, and this is going to be equal to 1, just because all of these here are going to be equal to 1. Now, it's very classical that each one of these integrals, e to the minus pi x squared dx, and on on R in one dimensions, is just going to be 1. Okay, so, and actually what we'll really use, it's just a lot more convenient for us, as we'll see, is we're going to actually use f square root of lambda, so it's going to be n over 2 square root of lambda as lambda goes to positive infinity. Okay, so let's start this whole kind of game here. So to really get this whole thing started, I need to know the Fourier transform of a Gaussian. And the claim is that Fourier transform of a Gaussian, e to the minus pi x squared, modulus x squared, is just itself. And I'm going to use complex analysis to do this. The proof, so it's nothing more than Cauchy's theorem, that if you take an entire function, integrate it over a closed contour, you get 0. That's all the depth of the complex analysis used here. So first of all, write down Fourier transform. Okay, and this here obviously is u1 squared plus dot 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 u n squared. This one here is going to be x1 u1 plus dot 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 xn un. All right, so use the properties of exponentials, and this is why this is very amenable to complex analysis, particularly just contour integration. Well, it just becomes this product here. When you integrate, you can do this in any order. Fubini's theorem. This is obviously L1 here. So this is just going to be the product of these one-dimensional, and I forgot the I here. I'll stick the I here. Sorry, the i's are here. So 2 pi, I'll stick the I here, and I forgot the I here. But anyway. So, right, what we have here, sorry about that. What we have here is just a product of one-dimensional Fourier transforms. Each one of these is just the Fourier transform of e to the minus pi x squared. Here it's x1 plugged in, xn plugged in. Well, this is just a product of the Fourier transforms if we can prove this lemma for dimension 1. And then this just becomes e to the minus pi modulus x squared. Again, this is contingent on, you know, this equals this equals this, which is just a one-dimensional case. So let's prove the one-dimensional case. Let's prove that these two are equal. Let's prove that these two are equal. So let's use the entire function e to the minus pi z squared. let's look at this contour here. So here x is fixed. Okay, and right, so here r is something large and positive. So Cauchy's theorem says this whole integral here is 0, not very deep. All right, so let's write out what this integral is. Well, here on the bottom, z is just t, so it's e to the minus pi t squared from minus r to r, and let r go to infinity. So this is actually a very clever proof, I should mention, or way to prove this lemma. Okay, so on top, maybe make this a little smaller. Right, so on top here, this point here is ix. So on top here, z is going to be just t plus ix. Well, t goes from r to minus r, so minus is going to be from minus r to r, hence we have the minus sign here. Okay, well, the right-hand side, z is going to be r plus it for t from 0 to x. This point right here, obviously, is, well, it's r plus ix. This point here is minus r plus ix. So the next one here is going to be, well, it's really minus r plus ix to minus r, minus it. It's going to be minus r to minus r plus ix. So it's just, z is just minus r plus it from t goes from 0 to x. Now, these two go to 0 as r goes to infinity, positive infinity. Just because you take absolute value inside, use the ML inequality, x is fixed, r is going to infinity. So both of these integrands behave like e to the minus pi r squared and modulus. Right. So you do get a e to the minus pi r x term, basically, but for fixed x, the e to the minus pi r squared absolutely dominates that and makes the whole thing go to 0. So it's very trivial, very easy to get that these two go to 0. So let's say this whole thing is a minus b plus c plus d. C and d go to 0, as I mentioned. So b is just this whole thing here. Well, sorry. So this whole thing here is b. Okay, so a is 1 as r goes to infinity, because we did this a second ago. It's minus infinity to infinity, e to the minus pi t squared dt, and I mentioned that's classically 1. So we got 0 equals 1. I should say, so everything is as r goes to infinity. Right, so we have, as r goes to infinity, 0 is minus 1. Sorry, as r goes to infinity, 0 is 1 minus b. So as r goes to infinity, b is going to be equal to 1. Okay. So you gotta stick limits here. But anyway. Right, so let's just expand out b. So when I do this here, it's minus pi parentheses t plus ix squared is minus pi parentheses t squared plus 2 tix minus x squared. So that just becomes minus pi, e to the minus pi t squared, e to the minus 2 pi I x t, and then e to the plus pi x squared. Well, I can, pull out the e to the pi x squared, and as r goes to infinity, this is literally the Fourier transform that we're looking for. So I guess it's, it makes sense to look at this e to the minus z squared and look at this contour, because on the top we basically get what we need. But anyway, so this is, we factor out the e to the pi x squared times the Fourier transform of x, which we said was 1. Fourier transform of f at x. F here is e to the minus pi x squared. So just divide everything by e to the pi x squared, we get exactly what we needed. Okay, so let me make a trivial observation about the Fourier transform, and in particular, if I take x over lambda, I take its Fourier transform, well, all I gotta do, and there should be minuses here, sorry about that, so easy to forget a minus sign when doing Fourier transforms. But anyway, so this is going to be, we'll just do v is u over 2, u over lambda, it's not 2, it's lambda. And then you get lambda to the n, and here it's u lambda when you do your substitution, your change of variables, but it's just a dot product, so we can bring it over to the first variable. And this is nothing more than lambda to the n times the Fourier transform of lambda x. So in particular, if g lambda is e to the minus pi over lambda modulus x squared, and here g1 is just a Gaussian whose Fourier transform we know, lambda is 1, then its Fourier transform, so I should mention this is going to be g1 of, maybe I'll put a little bar here. This is going to be g1 of square root of lambda x. Because it's, x over lambda. Okay, because square root of lambda, sorry. And it's square root because, well, you take out the, you square it, you get lambda. Okay, so we're basically using this, replacing lambda with square root of lambda, so it's lambda to the n over 2, g1 hat of square root of lambda x. That's exactly what this says here, replace lambda with lambda, square root of lambda. And the Fourier transform of g1 is just g1. So, right, again, you square the square root, it's e to the minus pi lambda x squared. Okay, so let's prove the isometry property. Let's prove Parseval's theorem. Okay, so first let me make a trivial observation. So I don't know if this integral converges. I don't know, rather, if modulus f hat of x is L2. It's certainly a measurable function. It's well defined. F is an L1 intersect L2. So as I mentioned in the previous video, the Fourier transform is well defined because by definition, let's just go back real quick to the definition here. Right, so here, very trivially, you put modulus inside. So if f is an L1, then this integral makes sense. Okay, so this is a measurable function. It makes perfect sense. But we don't know if it's an L2 or not. That doesn't matter. The monotone convergence theorem still applies. So we're applying the monotone convergence theorem with respect to this sequence of functions right here. So j are integers converging to infinity. So clearly this family right here is monotone increasing. And in the limit, this is just e to the 0 is 1, pointwise limit. So because this is monotone increasing and increases to 1, we get that these two are equal by the monotone convergence theorem. So let's do something clever. It's clever to first approach the Fourier transform. And we're going to use Fubini's theorem and hope nice things come out of it. And we're throwing this into the mix because we're going to try and get the Fourier transform of this to appear when we do Fubini's theorem. Okay, so right, so f hat of u actually is going to be with a minus here. So right, so here, let's see. Well, okay, so right, so I'll just make this a plus here. Right, so it's plus e to the 2 pi I u dot y. Okay, right, so let's plug everything in. So it's minus u dot x, it's plus u dot y, so we can combine everything into really this integral here over r 3 to the n. So we got the original integral over u, e to the minus pi over j modulus u squared. This integral, just integral f of x, and again, sorry about that. Get rid of this. Right, so this is the minus 2 pi I u dot x here. I rewrote it as x dot u, but that's fine. And here the minus is canceled to be e to the 2 pi I u dot y. I wrote it as y dot u. Okay, so let's use Fubini's theorem. This is certainly L1. Everything here is L1 in 3 variables. F of x, f and f are both L1 functions, and you can integrate this here. Modulus just gets rid of this complex exponential here, so everything is fine to use Fubini's theorem. It is obviously integrable in u for fixed j. So let's do the u integration first. Okay. And we definitely want this minus here because this is just a Fourier transform of this Gaussian. And we just found that out. Well, instead of j, we did lambda. So we, replace lambda with j. We got the Fourier transform of e to the minus pi over j modulus x squared as j to the n over 2 minus pi j modulus x squared. Okay, so that's where the j to the n over 2 comes from. But we're taking the Fourier transform, plugging in x minus y. And so it's e to the minus pi j modulus x minus y squared. So, right, this is the Fourier transform of this here with x minus y plugged in. So that's why it's an x minus y. I mean, here, it's just, here, the Fourier transform of this, it's just with the x here. Okay. Anyway, so this puts us in a really nice position because this is exactly this is basically this is convolution with f. Well, actually, so without, except for the complex conjugate, this is just f convolved with this approximate identity that we're dealing with. Okay, so let me just go back and show you that. Okay, so right, so here, well, yeah, here we're going to use square root of lambda, or really j, but anyway, so yeah, let me go back here, erase some of this here. Okay, so plug in j. So, well, I mean, yeah, so it's j over n, square root of j. So in this case, let's say we have f is this Gaussian that we were interested in a moment ago. So e to the minus pi modulus x squared. Okay, so this is true. This is true also. Right. We just have that on the next page. So get rid of this here. Place it with j, or rather square root of j. And this is going to be here that. Well, so we know exactly what this is. It's, well, just in general, remember it's going to be f square root of j of y dy. So now I need it in a different way. So you just do a substitution of u is x minus y. So y is going to be x minus u. And so plug in for what f square root of j is. In this case, f is e to the minus pi modulus x squared. This is going to be j to the n over 2 f of y e to the minus pi j. Actually, put the j first. X minus y squared dy. Okay, so this quantity here in LP, in particular in L2, converges to f as j goes to infinity. This is exactly what I have here. Okay, This is exactly what I have here. What I have here, except for a complex conjugate, is exactly, well, it's not exactly. I mean, instead of f here, I have, well, no, it is exactly what I have here. It's f of y e to the minus j times this here. Okay, so, right, so this converges to in L2, it just converges to f of y. Well, maybe, right, so I'll make it square root, just from what I talked about before. Right, and this is going to be modulus f squared. It's f of x, f of x bar. And because this converges in L2, you can check very easily that, you know, we have this converges in, I mean, we have this convergence here of integrals. That's very easy to check. It's just Cauchy-Schwarz inequality. I'm just writing this as f of x, f of y bar. So yeah, you would just do Cauchy-Schwarz, take this minus this, and modulus, smash in modulus inside, and then, or yeah. So these integrals converge, and that's exactly what we need to prove. That the L2 norm of f squared is the L2 norm of f hat. Okay, and the proof of Fourier inversion is similar. It's a little quicker, actually.